Okay, so this is our presentation on our project on floating point precision in GPUs. My name is Jeremy Myers.
And I'm Jacob Alter.
Okay, let us get started. As a background consideration, we must keep in mind that memory transfer is a major bottleneck in GPU programming.
Yeah, we've seen that in our own projects. I mean, looking at the results of NVIDIA profilers, even for basic stuff like vector addition, a lot of the time we could spend doing some more complicated computations, we have to wait for the memory to come first.
And so we do see this this bottleneck in a variety of different applications, but in particular, we see this a lot in machine learning tasks, which feature GPUs quite heavily.
Yeah, for example, I mean, if you're trying to train on some giant image data set, we're talking about millions and millions of images here. A lot of that time you're going to spend transferring the images to the GPU, going back and forth, and it's a huge issue.
So in order to reduce some of this overhead associated with data transfer between the host processing unit and the device, many people in industry and in research are using 32-bit rather than 64-bit floating point representations.
Yeah, and so there's been a lot of research that has gone into what kind of quantization schemes are best for neural network training in particular. Some people have used fixed precision schemes, some people use kind of mixed precision schemes. And NVIDIA has noticed this and has actually increased hardware support in their recent models, in particular the NVIDIA Volta, for these more complex schemes.
Right, and when we mean quantization schemes, we're talking about not only the data, but we're also talking about the processing that goes into it. So in particular with machine learning tasks, we're going to be focusing on neural networks, and this involves a variety of different types of matrix multiplication, activation function, weights that are associated with the different layers that are a part of the neural network. So these quantization schemes take into account different numerical representations for each different component of the neural network.
And one other important consideration a memory has is that, I mean, if you're talking about doing this on a data center level, energy efficiency is very important. And, well, whether you're talking about the data center level or the embedded systems level, the data transfer takes up a lot of energy, and that's something that needs to be monitored and studied more deeply.
So a question that we are going to investigate is how much precision is needed for accurate prediction. For some classification tasks, potentially just 1 bit, but this is what needs to be investigated.
Yeah. And yeah, in particular for generating a prediction from a neural network, all we really care about at the end of the day might be a 0-1 kind of thing. But the effect of precision on training is more of a question, because how this quantization, how it affects the training of the neural network, it could lead to different convergence to different areas of the error space, or some people think that using lower precision quantization could actually improve neural network performance by adding a certain kind of regularizing noise. And our kind of approach is trying to see, is this true? Will it improve network performance or lower it?
Yeah, especially since there's a variety of different training models out there. This is really important to understand. If Jacob's point about convergence to different local minima is very important, since you have techniques like ridge regression and lasso and stochastic gradient, where it really does depend on where the algorithm takes you in the convergence, and that absolutely impacts the outcome. So what we have done thus far is looked at a header-only implementation of a deep neural network called TinyDNN. And this is a platform to evaluate deep learning models. And we wanted to implement it for a range of data type precisions. So this is the first component of what we've looked at, is whether or not we actually can take something, a simple model, and be able to evaluate it at different levels of precision and just see how some of these factors, the accuracy in the testing phase or memory consumption or runtime, how these factors are impacted. So we implemented the Linnet-5 neural network for digit recognition on the MNIST data set. It's a standard in machine learning industry for training and testing, and found that accuracy between single and double precision floats was just about the same. Runtime was just about the same for both of these different data types. Unfortunately, it was a goal of ours to implement this for lower precision data types, but and we had some understanding that maybe it would work, but it doesn't. There's no evidence to say that TinyDNN supports anything lower than the single bit precision. We tested on half-size floats and on various integer types, but TinyDNN does not support any of these, and to appropriately implement them would require a fair amount of engineering and changing to the source code, which seems beyond the scope of this project.
So our next steps are going to use the cuDNN framework, which is lower level and gives us more of the flexibility that we need. This framework in particular is developed by NVIDIA for their graphics cards, and it's part of their deep learning software development kit. It's very widely used. It's a component of a lot of higher level machine learning frameworks like TensorFlow and Theano. And so it implements up a lot of the basic operations that we need to implement a neural network, like that linear algebra, like the activations that we were talking about. And it does offer extended support for 16, 32, and 64-bit floating point arithmetic. And yeah.
So where are we going with this? We are going to take this cuDNN framework, and we would like to train it on multiple data sets with varying levels of precision. So we propose training on the MNIST, the CFAR 10 and 100 data sets. These are just other image recognition data sets of different types.
And we have some images of them here. Here's MNIST, which is kind of a classic machine learning data set. It's, I think, tens of thousands of images of handwritten digits. There have been a lot of existing benchmarks on this, and it's frequently used for testing new machine learning models. And the other one we have is Cypher 10 here, which has 10 different classes of color images. Color in particular is important for us because, it's 3 channels, 3 times the data. So transferring that in between the host and the device is going to be a huge bottleneck.
So we want to ideally train on these different data sets with different levels of precision and evaluate on different neural network topologies. A couple of examples are CAFnet, there's Linnet, like we've tried already, ConvNet. There's a variety of different topologies that are out there. Obviously, we don't want to increase the parameter space too large. So we will do a bit of a review to determine what will be the most realistic and most helpful and informative topologies that are out there.
In particular, changing the depth of the network is something that we want to look at because the deeper networks, we expect that we might need higher precision because sometimes the gradients towards the end of the network can get, it's called the vanishing gradient problem. And so for lower precisions, these kind of very small signals in training might get lost. So that's something very important that we want to
That touches back on the stability argument that we made previously. But in addition to these levels of precision and the parameters that we're going to vary, we just want to look at the performance. Obviously, training and testing accuracy is a major consideration, and the training and testing time. Those are two key features, but transfer time between the host and the device and energy consumption. These are all very, very useful pieces of information, not just on the large scale, but also on small embedded devices.
So that's just a short overview of our project.
There you go.
Yeah.
Thanks.
Great.